Folks, welcome back to Skybound on the Ground with Michael Lombard. We are on to Chapter 11 of the Pilot's Handbook of Aeronautical Knowledge, and today we are talking about the weather. And as that famous quote is, everybody likes to talk about the weather, but nobody does anything about it. Well, guess what? You and I are going to talk about the weather because we can do something about it. We are going to be pilots, and we need to know what we can do about the weather so that we have successful flights. Alright, so weather theory. First of all, why in the world do we have weather? This is a good question, and it actually comes back to the same principle of why do we fly airplanes with wings on them? Why don't we just fly rocket things around? That's because, well, we have an atmosphere. Would you have weather on the moon? No, there's no weather on the moon. You don't have clouds and rain and all that stuff over there. That's because there's no atmosphere. We have wings that we can fly through the atmosphere, and that very same atmosphere also produces weather. Just a little bit of review of what our atmosphere is made up of. If you remember looking at the pie chart, the atmosphere is about 78% nitrogen gas, which is that inert gas, and that actually helps keep things from just spontaneously igniting, because that would be a bad situation for us Earthlings. And then 21% of it is that life-giving gas called oxygen, and then the rest of the 1% is stuff like argon and noble gases and whatever trace gas that you have, carbon dioxide and stuff like that. This is dry air, though. This is standard dry air. On any given day, you're going to have some type of moisture in the air, and it can account for up to 5% of the total volume of the air can be water vapor, and water vapor is responsible for the weather that we get. Now, the atmosphere also has weight, and if you were to be able to weigh the atmosphere, first of all, how tall is the atmosphere? The atmosphere goes up to about 350 miles. It's kind of hard to measure exactly where it ends because it just keeps on getting thinner and thinner, and you just have one or two molecules up there. But the atmosphere goes, they say it's about 350 miles. If you could take a square inch column that goes all the way from 350 miles down to the surface and put that on a set of bathroom scales, how much would the air weigh? It has weight because it has mass and gravity is working on it, so you would actually be able to weigh it, and this column of air would weigh about 14.7 pounds. And that is the atmospheric, so that's atmospheric pressure causing that weight right there. If you go up to, say, 18,000 feet, the weight of the atmosphere is actually half of what it is at sea level, and so that would be 7.4 pounds up there at 18,000 feet, and it keeps on getting less and less as you go higher. Now, when we're flying and stuff, we actually refer to the atmospheric pressure or the weight of the atmosphere in terms of inches of mercury, because remember, what we can do is we can have a tube of mercury and have that in a dish, and then see how much how far the mercury climbs up inside that hollow tube to measure atmospheric pressure, and it will go up nearly 30 inches when you're at sea level, and that will be 29.92 inches of mercury. Okay, so the atmosphere has weight, and there are also layers to our atmosphere. You can think of the atmosphere as you can think of it as kind of like different coats that we have on our planet, and let's take a look here. Here is our planet right here, and the first layer is called the troposphere, and this extends up to about 20,000 feet over the poles, and it goes a little bit higher over the equatorial regions, and so it's kind of gives it an oblong shape like that, but we call this layer over here the troposphere. And the troposphere is where pretty much all of our weather happens on the Earth. This is where you have the clouds and the rain and all the precipitation and snow and stuff. This is where it all happens right here. So let's just draw some clouds and stuff like that. And then above the troposphere is what you have is called the stratosphere. And the stratosphere, there isn't a whole lot of action that goes on. Here, let me write that a little bit closer this way so you can actually read it. Stratosphere, there isn't a whole lot of weather that goes on there. You do get some clouds that form that are able to go inside the stratosphere, but pretty much all the weather goes on down here in the troposphere. And the interface in between the two is what we call the tropopause. Tropopause essentially is this boundary layer between the two other layers, and this keeps it kind of keeps the weather inside the troposphere and from escaping out into the stratosphere. And the height of the tropopause will vary from season to season, and based on different whatever conditions you have during the seasons. And it's also associated with the jet stream. And so the jet stream will be oftentimes, around that tropopause area. Okay, so stratosphere goes up to about 160,000 feet. Once again, the troposphere extends to about 20,000 feet over the poles and 48,000 feet over the equatorial regions. And then up above you have some higher layers. You got the mesosphere, and then above that is the thermosphere. And these aren't really that important for us because they really don't have hardly anything to do with the weather that we're talking about. But those are the 4 layers of our Earth's atmosphere, and that extends up to, once you get out of the thermosphere, that pretty much ends at the 350-mile mark, and you're basically in space by that. Well, you are in space at that point. I think the space shuttle at the space station orbits at like 220 miles, roughly, or so. So anyway, that is our atmosphere. And now you remember that there was something called the lapse rate for temperature. As you go higher, if you go from sea level and you start going higher, for each 1,000 feet that you climb, you get about a 2 degrees Celsius decrease in temperature. While that lapse rate is relatively constant until you get up to the tropopause, and that is where you get into the stratosphere and the lapse rate stops. It stops getting colder, just kind of remains a relatively constant temperature as you go higher and higher. So lapse rate is really something that is part of the troposphere, and that is and that also has to do with the weather that we get. So also, what happens when you start going higher up and you get less atmospheric pressure? What does that do to your physiology? Have you ever been hiking up in the mountains and kind of noticed that you get a little bit short of breath if you go up higher? Well, if you keep on going higher and higher and higher, well, you eventually get to the point where you're not getting enough oxygen to supply your mental needs as well as your other body tissues, and you become hypoxic, where your body becomes deprived of oxygen. And you can actually start experiencing hypoxia as low as 10,000 feet. Some people who, especially if you smoke, you can experience that much lower, even down to like 5,000 feet. But hypoxia will impair your reaction time and your ability to think and do critical decisions and stuff. So as you go up higher into the atmosphere, you eventually have to start either using supplemental oxygen or having a pressurized cabin system. And that's why they always tell you about, well, in the event of a cabin pressure loss, oxygen masks will appear from the ceiling, and you have to put those on. That's because you're up there close to the edge of the troposphere. You might even be close, so because you are up so high, the oxygen is very thin up there. Okay, so now that is the air, that's the atmosphere. Now let's talk about the wind. And the reason why we have wind is because of the uneven heating of the Earth, as well as another factor. And really the uneven heating of the Earth is responsible for our weather all around the Earth. So if you look at the Earth right here, you will see that, well, first of all, it's on an axis, and as the rays of the sun are coming towards the Earth, it's the equatorial regions that receive the most heating, whereas the poles will not get as much of that heat, and so they're relatively cool, and that's why you have ice at the poles and stuff like that, compared to the equator where you can go around in shorts year-round. So if you're out here on the equator, it's going to be heating up more, and what that does is that heats up the air, and warm air gets lighter and it wants to start rising. You ever heard hot air rises? And yeah, you can think of several applications for that saying. But so the warm air at the equator tends to rise, and as it rises, cooler air tends to flow in from the polar regions. So as this equatorial air starts rising up, the cooler air from the polar regions starts coming in to replace it, and so you actually get this cyclic effect going on, this circulation, you could say, whereby the air is going up, and then as it cools down, it sinks down again towards the poles, and this cool air starts going back towards the equator. And so on a large-scale picture, this is in theory what should happen, but there is actually another force at work. There's another factor that we have to consider, and that's the factor that our Earth rotates. Okay, so what does that do to this circulation pattern? Well, if you were to compare our Earth to a merry-go-round, imagine that you are on the merry-go-round and you have a friend on the outside and you're on the middle there, and the merry-go-round is turning around counterclockwise just like our Earth does. And you have a ball and you want to throw the ball out to your friend over here. Okay, so let's do that. The merry-go-round is spinning around at a pretty fast rate, and so you throw the ball, and what happens is, well, it looks like the ball actually veers off to the side, but in reality, your friend has traveled this way while you threw the ball straight, and so by the time the ball gets out to the outside, your friend is way over here. And that's because of the spinning of the Earth. And if you look at the Earth, yeah, if you look at the Earth from the top, I was just going to have to move this around a little bit so you can actually see what's going on. If you look at the Earth from the top, say that's the North Pole, and here are the continents and stuff. It's basically like a large merry-go-round, and if you throw a ball, in this case, if you try to send the wind in a particular direction, the spinning of the Earth is going to alter its path in relation to where it was originally going. So if you have wind that's coming from the polar region and is heading towards the, here, let me just draw the example here again. And, okay, so there's your friend, and the ball, okay. And so if the wind is heading from the polar region towards the equator, it should go in a straight line, but the Earth is rotating, and so what ends up happening is it actually, in relation to the Earth underneath it, veers off towards the right. Okay, so that's interesting. What about the wind that is coming from the equator towards the poles? Well, this is a similar situation, but it's just the other way around. And now what's happening is your friend is on the outside here, and your friend wants to throw the ball to you now, and you're going to try to catch it. But as your friend throws the ball has this sideways or this angular momentum that's going on, and so instead of being able to travel in a straight line, even though he throws it straight forward, that ball has this sideways component, and so it actually heads off towards the right again. So the ball heads towards its right. If you throw it from the middle, it heads towards its right. If you throw it from the edge, it heads towards its right because of the rotation. And in the second case, it's because the ball already has this sideways motion. And so the same thing happens with the winds on the Earth. If they're coming from the equator towards the North Pole, they actually veer off to the right as well. And this is called Coriolis force. You will see this often when you're talking about large-scale wind patterns on the Earth. And in the northern hemisphere of the Earth, that causes winds to be deflected to the right from wherever they are traveling. If you're in the southern hemisphere, it's actually to the left because you're looking at it from the other way around. So that is Coriolis force, And it's actually pretty interesting because if you were to fire a missile or a rocket from one place on the Earth to another place, you actually have to take this into account, because otherwise you're going to land very far off target. So what this essentially does to the wind patterns is it creates three distinct cells of circulation on the Earth when you have this air that's heating up and circulating. So you remember we were looking at how it goes to the poles and comes back. Well, because the Earth is rotating and introducing this Coriolis force to the wind and causing it to rotate, as the wind is heading north, by the time it gets to about 30 degrees of latitude, which is about 1/3 of the way to the north, which is 1/3 of the way to the North Pole, it has come. It's made a right turn, and it's all the way. It's going all the way east now, and so instead of going to the North Pole, and then it keeps on doing its right turn, and so it just makes this circle that's is 1/3 of the way. And then if you go to 60 degrees, the wind that is up here is doing the same thing, and so you get these three distinct cells of circulation going on, and this is why we have the prevailing winds that we have in different parts. Now, of course, this is just very generalized, and it will be modified based on what kind of geography you have underneath the wherever the winds are, and also what the season is. So the atmosphere is extremely dynamic. It's always changing. There's all sorts of factors that are going on. But this is just the big picture of what is going on so that we can kind of start understanding how our atmosphere works. Now, while we're talking about pressure and winds and stuff like that, let's look at, well, this Coriolis force actually explains how winds tend to circulate around high and low pressure systems. First of all, what is a high and low pressure system? A high pressure system is where you have descending air over a large area. So you have descending air that is coming in, and it is spreading out and flowing out in relation to, it's just flowing out. Low pressure areas are where you have air that's rushing into a low pressure area and going up into the atmosphere. So it's kind of the opposite. It's the opposite opposite direction, high and low pressure. Okay, so you'll have these high and low pressure areas that develop over different parts of the globe, and what tends to happen is that you will have a very predictable way in which the winds circulate around these high and low pressure areas. If you have a high pressure area, the wind is flowing out from there, and remember, what does Coriolis force do to the winds? What direction does it bend them? It bends them to the right when you're in the northern hemisphere. And so that's why you actually get a clockwise circulation pattern around high pressure areas as the air is coming down towards the surface and it's spreading out. As it leaves, its direction gets turned to the right. If you have a low pressure area, you have air that is coming in towards the low pressure area, but it is being bent to the right as well as it is traveling. And so that keeps on happening as it gets closer and closer. It keeps on wanting to get bent to the right, and so what finally ends up happening is that you have this, it looks like it's bent to the left instead. You have a counterclockwise circulation that goes on around low pressure areas. And you can actually take advantage of this when you're going on a long distance flight. Say you're on the west coast somewhere and you want to go to maybe a Great Plains state or whatever, and you want to get tailwinds. So if you want to get tailwinds, you can fly to the north of the high pressure area and get that outflow that's pointing you in the right direction. Or if you want to get, if you're close to the low pressure area, you would just go south of it and you would get the advantage of the counterclockwise rotation. It would be pushing you in that direction if you go to the bottom of the low pressure area. Okay, so that is highs and lows, and you can take advantage of that. Now, you will also be able to see the show the pressure differences between the high and low pressure areas. They will depict them on maps, and the way they do that, it actually looks very similar to a topographic map that you have used for when you go hiking. You know how you have contours and stuff. So let's look at the high and the low pressure area again. So you'll have these an area of low pressure, and they will depict contours on a map. And say it's like 1,005 millibars. That's another way of measuring atmospheric pressure. We can do it in in inches of mercury, or you can do it in millibars. And the standard pressure at sea level for millibars is 1,013.2 millibars. So say we have this low pressure area, it's 1,005, and then as you get further away from the low pressure area, the air pressure starts increasing as it gets closer to the high pressure area. So maybe over here it's like 1,010, and then it keeps on getting higher. And you can see that these contour lines represent the different pressure levels, and it's kind of like going uphill or downhill, and that is how you can read it. If you have contour lines that are really close together, that tells you something important. That tells you that there's a steep pressure gradient, and therefore you're going to have strong winds over there, because the wind always flows from an area of high pressure to an area of low pressure, and if you have a steep gradient, that wind, it's kind of like going downhill, a steep downhill, and so the wind is going to flow a lot faster there. Now, when you have the, remember we have the general direction that our wind circulates. It circulates in a clockwise fashion around high pressure areas and a counterclockwise fashion around low pressure areas. That is when you have the wind that is above 3,000 feet above the surface, when it's high over the Earth, and the Earth isn't interfering with its circulation. But if you look at the air that is very close to the surface of the Earth actually has friction, and it interferes with the air, and so it will tend to flow across the isobars. Sorry, I'm pointing that arrow in the wrong direction. It'll flow in a straight line more so, but when you get higher up, then it will tend to go parallel with the isobars and be deflected by Coriolis force. So that is our general circulation patterns that you get with the winds when you have high and low pressure areas. And you can also remember that high and low pressure areas are associated with different types of weather. Generally, high pressure is dry, stable air that's coming in, and it is associated with generally fair weather. Low pressure areas, you've probably heard, oh, the barometer is rapidly falling and we're getting a hurricane or something like that, and low pressure areas are often associated with poor weather. You have precipitation and cloudiness and all sorts of stuff like that. Okay, so as we are continuing to talk about winds, we were just looking at the large scale picture. Let's go and look at something that's a little bit smaller scale, something more local. If you are flying along and you obviously are going to have different terrain features that you're flying over. You might have like a lake or something, and then maybe some forest or trees or vegetation on the other side. Actually, let me put this a little bit further. Maybe you have some rocks and stuff like that, and then some forest and trees. So these different terrain features absorb the sun's heat at different rates, and in turn they give off heat at different rates as they get hotter. The water tends to absorb quite a lot of heat and not give a lot of heat off, whereas the rocks and cement and stuff like that tends to give off a lot of heat. And then again with the vegetation and stuff, that kind of keeps things cooler. So as it gives off heat, it warms up the air around it, and that air starts to rise. And so you get a difference in the air currents that are close to the ground, especially on hot summer days. And so you get what's called convection currents. And these convection currents produce bumpiness and turbulence as you're flying along. And so you will notice that while you can fly over some rocks and stuff, you'll get these updrafts, and then you come over a water body, and then suddenly you find your airplane kind of sinking a little bit, and that's because you don't have that rising air anymore. So you'll notice that you get turbulence on when you're close to the ground, when the air is heating up and rising. You can actually get above that turbulence by seeing where the cumulus clouds are, those puffy cotton ball type clouds, and just flying above them because the air will be smoother up there. And then you also have to be careful if you're coming into an airport and you are experiencing updrafts, and then you come over the lake, and then suddenly you realize that your airplane is starting to sink down lower than what you wanted it to experience. You just have to make sure that you compensate for that, and that it doesn't take you by surprise when you're at low altitude. Okay, so that is convection currents. You also get some wind circulation that is a very predictable pattern when you are by a large body of water. Think like the beach. So let's say we are at the beach today, and you have it's daytime, and the sun is heating up the land and the water, but they are heating up at different rates. The water tends to heat up slower, and the land heats up quickly, and it starts giving off all that heat and heating up the air around it. So the air that heats up rises, and the cooler air that's over the water comes in to replace it. And as the air that heats up rises, it cools, and then it goes down and sinks over the water, and then you get this circular circulation, this pattern going on, and this is what we call our onshore breeze. And you will notice it pretty much every day at the ocean. It's very predictable. You get this onshore breeze because of the uneven heating of the land and the water. Now, let's turn off the lights and make it nighttime. Well, we'll have a little bit of light because we'll have the moon up here. Okay, and what happens at nighttime? The land cools down rather quickly compared to the water, and so now the water is heating up the air around it, and this air gets hotter relative to the air on the land, and the air on the land starts flowing out, and so you get the circulation, the cycle continues, and it gets reversed. It goes in the opposite direction, and so at nighttime you get the offshore breeze, and so the air flows from land towards the offshore direction. And so it's pretty cool. You will notice this happens. It's very predictable, and so that is what you get by large bodies of water. Now, there is something else that you'll also notice with wind patterns, and that is when you have obstructions to the wind flow. If you have ever looked at a river, you'll notice that the rocks and stuff that you have in the river cause the water to flow. You get the rapids and stuff, and you get these eddies and whirlpools and stuff, and the wind is exactly like a river of air. If you put rocks or big things in the way, it's going to start swirling around. So this can have consequences for if you have an airport, and say there's a runway over there, and you have buildings nearby. Let me try to draw, have good buildings. So whatever stuff you have nearby in the way, maybe a silo, as the wind is flowing, it's flowing this direction, it'll come over here and it'll kind of get, it'll swirl around, and so you can get these currents and stuff that kind of really mix up your game as you're trying to land. And this is caused by the obstructions, and the amount that the wind gets disturbed really depends on the size of the obstruction. Hopefully it doesn't cause destruction. Size of the obstruction, as well as the velocity of the wind. If you have high winds, that'll do a lot. If you have large obstructions, you can also have little hills. I know that there's a hill that is in the way of the approach, or just off to the side of the approach for runway 25 at my home airport of Auburn, and the wind that's coming over there always creates this funny, squirrely effect of wind as you're trying to land the airplane there. And you also get this problem when you're in the mountains, and it's on a larger scale, because if you have air that is flowing this direction, it'll go up the mountain, And then as it comes up over, you have all this turbulence that goes on the other side, on the leeward side of the mountain. You can get these strong downdrafts. You get an updraft on the windward side, and then you get strong downdraft and all sorts of turbulence on this side over here. And so that's why when you start flying, don't go and fly in the mountains unless you have an experienced instructor with you who can teach you the ins and outs of mountain flying. And this especially is the case when you have strong winds flowing over the mountains. So this is the this is the mountain. This is what happens when you have mountains and obstructions and stuff. And we have one more thing that we need to take a quick look at, and this is an especially hazardous hazard. And this is called wind shear. Now, wind shear, simply put, is a large change of direction or speed of wind in a short space. So you might be flying along, maybe you are transitioning your altitude, and up here the wind is flowing along at, say, 40 knots, whereas down here it was only going at 5 knots, and this is just maybe like 1,000-foot change. And so this is called wind shear, and this is actually a horizontal type of wind shear. And the wind could also be, maybe it could have changed directions. Maybe the wind was flowing in that direction, and you go up here. Well, this has implications for aircraft performance, because if you were originally flying with a headwind and then you climb up just a little bit and suddenly it turns into a screaming tailwind, that is going to reduce your aircraft performance very quickly until you're able to regain your airspeed in that air mass. And so that is very significant if you are at low levels. You can also encounter vertical wind shear, where you get updrafts and where you get downdrafts and updrafts, and those can push your plane towards the ground or just raise your plane up very quickly. So you get horizontal and vertical wind shear, and you can encounter wind shear at any altitude and pretty much on any day. But when it's most hazardous is when it is close to the ground, and it will often be associated with thunderstorms and frontal systems that are passing by, as well as temperature inversions that have strong winds on top of the temperature inversion. By the way, a temperature inversion is when it is colder at the bottom, say maybe 0 degrees centigrade, and you climb up and it's 10 degrees. It's basically where the lapse rate is opposite. It's flipped over of what it's supposed to be. So if you have strong winds on top of the temperature inversion, maybe like 30 knots or something, then you're going to notice this wind shear effect, because the winds down below are probably going to be pretty calm. So yeah, you will have wind shear associated with thunderstorms, temperature inversions, and frontal systems that are passing by. This is most hazardous when you're close to the ground, because you are needing to have every ounce of your aircraft performance when you are landing or taking off, because you're operating right at the edge of your performance envelope. You don't really have a lot of extra power to play around with. Maybe you don't have any extra power. And so here is the most hazardous situation that you can encounter, and it's called a microburst. Now, microbursts are very strong intensity downdrafts that typically last less than 15 minutes, and they only are in like about a mile radius, and they usually happen right around thunderstorms. And so you have these strong winds that are coming down, and they come down at velocities of up to 6,000 feet per minute. And folks, airliner aircraft can't climb that fast, and so there really isn't many airplanes that are, you don't have airplanes that are immune to the dangers of this. If you happen to encounter this close to the ground, you might be pushed straight down into the ground unless you have enough altitude to get around, to compensate for the amount that you descend. So what you will notice is that as you're flying along, say you are just taking off here, and you get as the wind gets close to the ground, it spreads out in all directions. And so you will notice this increasing headwind, and it's like, oh wow, the airplane suddenly feels like it's flying really fast, and it's got all this lift that it's able to produce. And so the airplane will start increasing. Will start increasing its performance, experience an increase in performance, and it'll start climbing. But then, as you get to the middle of the microburst, now you're experiencing the downdraft effect, and it starts pushing the airplane down towards the ground. And to compound things, it starts turning into a tailwind component, and all that lift that you were experiencing suddenly starts decreasing as the wind starts blowing from the tail of the airplane, and you don't have enough air flowing over the wings in the proper direction, and so the plane starts getting pushed down towards the ground. And so that is what you would notice. You would start getting a really bad decrease in performance on the other side of the microburst. Now, thankfully, these things last only about 15 minutes long, and they will have, at some airports, they have low-level wind shear warning systems to notify pilots if they are noticing these patterns in the area. And you can also see, well, if there's a thunderstorm in the area, well, don't fly around thunderstorms because you might have these things. You'll see areas they'll be associated with areas of very strong precipitation around this thunderstorm. Or you can also see maybe some virga, which is rain that looks like it's falling down and then it kind of evaporates before it hits the ground. And then if also you see, now virga isn't always microbursts, but if you're around like a thunderstorm or something, virga may be associated with the microburst. And then also you can have, if you see like just, if there's nothing in the air but you see like a ring of dust on the ground, oh man, that's something that you want to stay away from. So those are clues for spotting microbursts. But if you do encounter some type of wind shear that's close to the ground, what you want to do is just go full power and try to climb out of it if you can. This is the worst situation that you'll encounter, but you can also have less severe wind shear in which, as you're approaching the airport, perhaps you encounter more of a tailwind factor, and so that robs you of airspeed, and so you'll have to power up to keep from sinking. So be aware of wind shear and be always vigilant on what's going on. And now we have talked a lot about winds and pressure patterns and how stuff circulates, the big picture. Now, next lesson, we're going to find out a very important question, and that is, where do clouds come from? So join me next time as we continue exploring. We're going to do the second half of Chapter 11, Weather Theory, in the Pilot's Handbook of Aeronautical Knowledge. And we're going to continue learning about weather. So again, bring your umbrellas because we are going to figure out about clouds and stability of the atmosphere and all sorts of cool stuff like that. So see you next time.